Hello everyone, I'm going to go over lesson 6.6 with you, the trapezoidal rule and definite integral of rate of change. And this lesson is how to approximate the answer to a definite integral by finding the area under the curve using rectangles or trapezoids. So let's take a look at the do now. The table below represents the velocity, v of t, in feet per second of a car traveling on a straight road over a 50-second time interval. Use the graph in the table to approximate the area under the graph of v of t in 5 subintervals. But this is the key. What does the area under the velocity curve represent? Well, if we take a look at v of t, which is the y value, right? And that's the height of the rectangle. And the x value, the dx, is the change in time, delta t, right? Change in time. We have feet per second times seconds. And that gives us feet. So the area under the velocity curve represents the distance traveled in feet, okay, which is really nice, and it's really consistent because when we multiply height times width for the area of a rectangle, we have feet per second times second, which gives us feet. So the answer to this problem is that as long as the velocity is a positive, then it represents the distance traveled in feet. Okay, so let's approximate the distance traveled in feet using 5 subintervals. And there are 3 ways to do this: left ram, right ram, and midpoint ram. Okay, so we're going to try to do that. I'm going to do left, right, and midpoint ram all in one graph here. And then we'll go to how we can use trapezoids to approximate the area under the velocity curve. So if we use 5 subintervals, our delta x, well, n is 5, because that's 5 subintervals. Delta x is b minus a over n. So because a starts from 0 and b ends at 50, and we have 5 subintervals, the width of each subinterval would be 10. And I think you can see that if we wanted to make 5 equally spaced subintervals, the subintervals would be from 0 to 10, 10 to 20, 20 to 30, 30 to 40, and 40 to 50. And these are the subintervals we're going to use for all of the approximation methods: left, right, midpoint, and trapezoid. So I'm going to highlight this in yellow so we'll remember that. This is used for all 3. So the first thing we're going to do is we're going to slice up our region into these subintervals, but I'm going to branch them off in the chart this way. Okay, so we could see them. Those are from the chart, and on the graph, we're going to slice them up: 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50. Okay. All right. Now, for left ram, we pick the left endpoint in each subinterval. So I'm going to put that in red. So the left endpoint would be 0 for the first subinterval. That's from 0 to 10. The left endpoint in the second subinterval is 20. Zero to 10. Oh, I should say 10. That's the y value. So this is at 20, right? And then the left one from 10 to 20 is 20. which gives us 52 here. And then from 20 to 30, the left is 30, which gives us the 80. And then the left from 30 to 40 is 30. I'm sorry, from 40 to 50 is 40, which gives us a 77. And the sum of the areas of these red rectangles would represent the distance traveled in feet. Okay, so the definite integral from 0 to 50 of the velocity, because this represents the area under the velocity curve, is about equal to 10. We could factor out the 10 because it's the width of all the rectangles, of 0 plus 20 plus 52 plus 80 plus 77. So notice how we pick the left y values, okay? And this would give us 2,290 feet. I'll leave that up to you. But if you write feet here, this is a perfectly fine answer on the AP. You don't have to multiply it out, as long as you show what we're adding and the correct numbers. Now for right ram, I will do this in blue. We pick the right endpoint in each subinterval. So in the first subinterval, we're going to pick the 10. Which gives us the 20. Okay, in the second subinterval, we're going to pick the 20, which gives us the 52. In the third subinterval, we're going to pick the third subinterval is from 30 to 40. I'm sorry, the third subinterval, that's 1, 2. The third subinterval is 20 to 30, and the right endpoint is 30, so that gives us 80. In the fourth subinterval, we pick 40. That's the right endpoint. That gives us the 77. Okay. And the last subinterval is the 50, which gives us the 74. Okay. So the definite integral from 0 to 50, which is another way to represent the area under the velocity curve, is approximately 10 times. And now the right y values, which are 20 plus 52 plus 80 plus 77 plus 74 feet. But when we work that out, it comes out to 3,030 feet. Now, midpoint RAM doesn't involve averaging at all, okay? And that the averaging would only come in when we were doing the Riemann sum, finding the limit as n increases without bound. But here, if we have a chart and we don't have the function, we find the midpoint by looking at the middle term in each subinterval. So the best midpoint in the first subinterval would be, and I'll do this in green, 14. Okay, that would be at 5, because that's in between 0 and 10. So midpoint RAM would be here, which would give us our 14. And the next one would be 15. And the next one would be 25. And the next one is 35. So that would go up here somewhere. Notice that the marks are already there for you in black. And then 45. So here's 45. Okay, so for midpoint RAM, the definite integral from 0 to 50 of the velocity is approximately equal to 10 times 14 plus 28 plus 70 plus 86 plus 70 feet. And that comes out to be 2,680 feet. And notice on the chart, these are the middle y values in each subinterval. So remember, we always sum up the y values times the delta x, whatever that may be. Okay, so there we go. So please mark this off on your paper, on the chart as well as on the graph. All right, now trapezoidal sum, okay, is exactly what you would think. We slice up the region the same way from 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50, and what we do is we form these trapezoids. So this I will do in purple. To form a trapezoid from 0 to 10, we just simply connect the endpoints. All right, that's a triangle. So, but a triangle is thought to be a special trapezoid with no lower base. So this is the second trapezoid, and this is the third trapezoid, and the fourth trapezoid, and the fifth one. Notice the parallel sides of the trapezoid are these vertical line segments. The heights of the trapezoid is delta x. So recall that the area of a trapezoid is 1/2 the height times the sum of the bases. Well, because the height, these are the heights, are always 10, we could factor out here the 10, do 1/2 times 10, and add the bases. Well, actually, yeah, we could add the bases. So the sum of base 1 and base 2 would be 0 plus 20. But the second two bases in trapezoid 2 would be 20 plus 52. So notice that the upper base of one trapezoid is the lower base of the other. For trapezoid 3, the bases are 52 and 80. For 4, the bases are 80 and 77. And for 5, the bases are 77 and 74. So notice that these numbers here, the bases on the inside are always doubled, but the bases at the very ends only are counted once. So I could rewrite this trapezoidal rule as follows. 1/2 times 10 times 0 plus 2 times 20 plus 2 times 52 plus 2 times 80 plus 2 times 77 plus 74. So these are just the ends, the end y values. And the answer there is 2,660 feet. And if we compare midpoint left, right RAM and trapezoidal rule, we notice that the trapezoidal rule is probably more efficient than midpoint RAM, slightly more accurate in this case. So it turns out that if we average the left RAM and the right RAM, take the left RAM that we got and add it to the right RAM and divide it by 2, and this I really mean average. We have 2,290 plus 3,030 divided by 2. It turns out that it's 2,660 feet, which is exactly equal to the trapezoidal rule. It turns out that the average of left and right RAM always gives us the trapezoidal sum, and that's a good extra credit to prove. Prove that the trapezoidal rule, the trapezoidal sum, is the average of left and right RAM. Okay. A lot of students think that midpoint RAM is the average of left and right RAM, but it's not. It's a more accurate estimation for the area under the curve, and it turns out to be the trapezoidal sum. So let's just summarize here. Okay, so for the summary, we're going to summarize the trapezoidal sum. I should say the trapezoidal approximation. There should be approximation for the definite integral. And it's written this way, but, but this formula, note, works when the delta x is the same number. We will see in later examples that delta x does not have to be the same. And again, if we form these trapezoids, as you can see here, they were already done for you. This trapezoid doesn't even show here. We could say that the area under the curve from a to b of f of x dx is approximately equal to 1/2 the height times the sum of the bases. But the first base is f of a, the last base is f of b, and all the bases in between are doubled. Oh, so I should say 2 times f of x1 plus 2 times f of x2 plus 2 times f of xn minus 1, all the way down to f of b. And again, this is true when delta x is the same number. If delta x is not the same number, in other words, if the width of each subinterval is not the same, then we find the area of each trapezoid individually. Separately and add. And we'll do that very soon. Okay, now as far as an application is concerned, the net area, now this is the area under the graph of the velocity, which is the derivative of the position over the time interval, is called the displacement, right? This is area with a sign. So let's say I travel 6 units to the right and 2 units to the left. Then the displacement would be 4, but the total distance traveled is 8. So to get the total distance traveled by the particle, if v of t is not positive, that is, if the graph is not above the x-axis or the t-axis, we put absolute value around the velocity function. We didn't need to put absolute value around the velocity functions in the do now because the velocity function was already above the t-axis. So in general, the definite integral of a rate of change, because remember, the rate of change of a function, the rate of change of the velocity, the position, is the velocity. So this leads to a very important generalization. When we integrate over a time interval a derivative, right? it gives back the function, right? It's the total change in f on the time interval from t1 to t2. Okay, example, I'll write it down here. The definite integral from t1 to t2 of the derivative of the position function, which is really the velocity, is the total distance, the total number of feet traveled on the time interval from t1 to t2, right? But this is assuming that v of t is greater than 0. So the units for the integral of a rate of change is easy to find. We find the units for the derivative, which is always feet per second, multiply it by the change of delta t, which in this case is in second, and we get feet. So the units can be found if we analyze the units of the derivative and dt. For example, okay, let's look over here. Miles per hour times hours would give us miles. Cubic gallons per hour times hours would give us cubic gallons. Number of bananas per hour times hours would give us number of bananas. And these would represent a derivative. So when we integrate a derivative dt, we can always find the units. We could analyze it in terms of the context of the problem. Okay, let's take a look at the next problem. All right, so this kind of summarizes what we've done in the do now. The rate at which water flows out of a pipe in gallons per hour. All right, so again, those units are very important. Is given by a differentiable function, capital R, of time t. The table below shows the rate as measured every 4 hours for a 24-hour period. Okay, so it says Part A, B, and C all estimate the definite integral from 0 to 24, but they have different subdivisions. The Part A says, using a left ram with 6 subdivisions. Okay, so let's analyze that. If A is 0 and B is 24 and N is 6, then our delta X is B minus A over N. That's 24 minus 0 over 6. That gives us 4. So our units, our intervals are 0 to 4, 4 to 8, 8 to 12, 12 to 16, 16 to 20, and 20 to 24. Okay, which are these intervals, which I will loop off here. Now, if we use left ram, and notice delta x is the same, so I could factor out the 4, I could write that the definite integral from 0 to 24 of r of t dt is about equal to 4 times, that's our delta x times, the heights on the left. Okay, so what are the heights on the left? Okay, we're going to put this in yellow. 7.5 for the first subinterval, 9 for the second, 9.3 for the third, 9.5 for the fourth, 8.8 for the fifth, and 8 for the sixth. So let's add those up. Okay. Now, if we were to do the same number of subdivisions using right ram, Okay, all right, I should put this in yellow to be consistent. These are the right, these are the left. Now we're going to do the right. The right ones would be the right y value. So it would be all the y values except for the 7.5 because it's not on the right of anything. So we get 4 times 9 plus 9.3 plus 9.5 plus 8.8 plus 8 plus 7.2. Okay. For part C, we're using midpoint RAM, but here we have 3 subdivisions. So if A is 0 and B is 24 and N is 3, then delta X is B minus A over N. That's 24 minus 0 divided by 3. The width of each subinterval would be 8. So we have the intervals are 0 to 8, 8 to 16, and 16 to 24. All right, and I'm going to loop those off in red. 0 to 8, 8 to 16, and 16 to 24. So the y values we pick in these subintervals would be the ones in the middle, right? Whatever that middle y value is. So our approximation is eight times 9 plus 9.5 plus 8, because these are the y values in the middle. Okay, let me just put this in red, and let me put this in green, so we have everything consistent. All right, and finally, we're going to estimate the same using 3 subdivisions with the trapezoidal rule. Okay, now because delta x here is 8, we do the following. All right, so I wish I could show you the chart. Wait, let me see if I can make this smaller. Okay, so what we do here, and this is a little trickier, we do 1/2 the height, the height, which is delta x, and it's the first y value plus the second y value plus twice the second. Or you could do 7.5 times twice the second, which is 9.3. And then twice the third, which is twice 8.8. Okay, remember, this is 3 subintervals, not 6. And then the last. And that would be the answer with the trapezoidal sum. And then what does this all mean? Well, if we analyze it, this is gallons per hour times hours, which gives us gallons. So all of these estimate the total number of gallons that flow out of the pipe from t equals 0 to t equals 24 hours. Or we could say the first 24 hours. And even to be more precise, I think it was water, right? The total number of gallons of water that flow out of the pipe in the first 24 hours. And that's it. Okay, now in the next exercise, I have a 5 for 5. There are 5 problems that would represent what you would get if you were to take the AP. It's a cute exercise. This was created by one AP Calc teacher that's really popular in the AP world. His name is Brian Passwater, so I give him total credit for these problems. And I just wanted to do the first 2 with you to show you an example where delta x is not the same. A child is inflating a balloon by blowing air into it. Okay? Each time he takes a breath, a small amount of air leaks out of the balloon. The table above gives various times of various values for time t in seconds, and the derivative of r of t, the rate of change of the radius of the balloon, in millimeters per second. Okay, notice how the units are specified. Okay, use a left Riemann sum with 3 subintervals to approximate the total change in the radius of the balloon in the interval from 1 to 11 seconds. So if we're going to use 3 subintervals, the delta x is not useful here because notice that the width of the subintervals are not the same. Okay? In the 3 subintervals, if we wanted to divide it, would have to be these, the way it's given. 1 to 4, 4 to 6, and 6 to 11. You are not expected to do anything more with the chart. You go with what you have. So delta x in the first subinterval is 3, delta x in the second subinterval is 2, and delta x in the third subinterval is 5. So we do not compute delta x by the b minus a over n formula because that formula is only used when the intervals are of equal length, and they should specify that. So if we were to use left RAM, we would use the left endpoint, which is everything except the 3, which is not on the left of anything. So left RAM would give us 3 times 10, which would be the area of the first rectangle, 2 times -1, which is the net area of the second rectangle. It's probably below the x-axis, but that's okay. And because remember, definite integral is net area anyway. And the third rectangle is 5 times 2. So the answer to this would be 38 when we add it together. And technically, it would be 38 millimeters, right? Because when we multiply, we would get millimeters per second times seconds is millimeters. All right, here's another example. The graph of g is shown above where the derivative of g is greater than 0. Again, the sign of the derivative tells us something about g. G is increasing, and this is the graph of g, and g is increasing. The second derivative of g is less than 0. That means g is concave down, and certainly it has that concave down look, where x is greater than 0. If a right RAM is used to approximate the area between g and the x-axis on the interval from 1 to 5, which of the following is correct? Okay, so if I was to use right RAM from 1 to 5, okay, so I'm doing 1 to 5. Okay, it doesn't say how many subintervals. Okay, I'll just divide it up the way I have it. Doesn't tell me 5 subintervals. I'll make 5 subintervals. And if you use right RAM, then of course I use the right endpoint. So I'll pick the right endpoint here, go up. There's my right rectangle. Here I go up. There's my right rectangle. Here I go up. There's my right rectangle, and etc. Okay, so I've got a very nice picture of right RAM. All right, which of the following is correct? The right sum will be under the approximate area from 1 to 5. Well, obviously, the right RAM is greater than the area under G from 1 to 5. I mean, I think we can see that there's an overestimate here. So it's not this, and it can't be this either. It's not under, it's over. So which one of these is correct, C or D? The right sum will always over-approximate the area because the first derivative is greater than 0, meaning that G is increasing. All right, that's possible. Or the right sum will will be an over approximation of the area from 1 to 5 because G is concave down. Well, which one do you think is a more powerful argument? When G is increasing, must right ram always be an over approximation? Or when G is concave down, must right ram be an over approximation? Well, if we think about it, if G were concave up and increasing, which we could do it this way, and we subdivide it in the same way, and use right ram, oh, wait, is that right? Wait, this is concave up. Right ram. Oh, no, right ram is this way. Oops, I drew this wrong. I knew I did this wrong. Okay, let's do it again. So if G is concave up, like this, and we use right ram, okay, and I started subdividing this and used the endpoint on the right. Well, it looks like it might be an, let's see, something doesn't jive here. I think that the correct choice is C, because it's increasing. And, oh, I see. Yeah, okay. If we want to know if right ram is an over or under approximation, the reason would be more so for the increasing decreasing behavior, because concavity is only an over or under approximation of the tangent lines. Over, under, for tangent lines. Not for the left and right rams. Left and right rams can be determined more so from just the increasing, decreasing behavior. So so C would be correct. Because G is increasing, and we always look at the increasing, decreasing behavior to see whether or not a ram is an over, under approximation. And then finally, I'm going to leave you with 3 and 4. I'll leave 4 and 5. I'll have you do by yourselves. The average value of a function I didn't teach you yet. But I will give you the formula so you could answer the question. And that's 1 over b minus a times the definite integral from a to b of f of x dx. All right. So try 3 and 4 and 5 by yourselves, and I will provide you the answers when I assign the video. All right, everyone, have a wonderful day, and I hope everything worked out well. All right, take care. Bye.